So we begin today exactly from where we ended the last class. That is to see how the energy level of an isolated atom is affected when another atom is gradually brought close to it. So for this, we consider two hydrogen atoms, the simplest of all atoms, which have only one electron. So as we know that the hydrogen atom, the electronic state, ground state is 1, can be identified as 1s1. That means the principal quantum number is 1 and the subshell is s, that is L equal to 0, and only one electron occupies that level, although its occupancy is 2, that is 2L plus 1 into 2 is the occupancy of the state. So this is equal to 2 into 2 into 0 plus 1 equal to 2. So this is the ground state of the electron. So this is my hydrogen atom, this is the nucleus, which is 1 proton, and this is the electron which is orbiting the proton, and suppose the radius the orbit is r0. Let me draw it little. So this is the electron, this is the nucleus, and this is the radius of the orbit, which we call r0. And suppose this is the ground state, energy state of the electron, so which is denoted as 1s1, ground electronic state, hydrogen atom. Now this is for the isolated atom. Now we want to see if we bring a second hydrogen atom. A second hydrogen atom, it also has its electron, proton, and we bring it closer to this first atom. This is my first atom, and this is the second hydrogen atom. We are bringing it closer to this, and we call this separation as R. So we want to basically find out how this energy level is modified, is affected as we gradually bring this second atom close to the first atom. So we basically plot, this is my R, the separation between the two atoms, and this is the energy. So the isolated atom has this much energy. So this is true when R is much more than 2R0. 2R0 is the summation of the radii of the two atoms. So that means when the two atoms are widely separated, then the energy level is just what would be for an isolated atom. Now what happens when, say, at this we say that R is nearly equal to 2R0. That means, you see, the electrons have its own wavelength, and therefore it has associated wave function. So that means when R becomes nearly equal to 2R0, that means the two atoms are just touching each other. That means the wave functions have started overlapping. So what happens to the energy level then? See, when the two atoms, at this point, the two atoms are kind of touching each other. So we might as well say that the wave functions are overlapping. That means that the electron, each electron is now revolving around both the nucleus. This is equivalent to saying that the energy level at this point where R is nearly equal to 20, the energy level is split into two levels. So that is when two atoms are brought close to each other. So then if we bring four atoms instead of two atoms, if we now bring four hydrogen atoms close to each other, so then it is easy to visualize that the energy level will now split into four different energies. So that means the four electrons can actually rotate around all the four. So they have started interacting with each other. So that manifests the splitting of the energy levels. So if we have n number of atoms, then there will be splitting. If we have instead n number of atoms, so it will split into n number of energy levels. Now so that's all. If there were four atoms instead of two, energy levels would then split into four as the number of new levels equal the number of interacting atoms. Generally speaking, therefore, if n atoms are brought together, the energy level would split into n separate levels. In a solid, an exceptionally large number of atoms are packed in a tiny volume. And consequently, the levels come so close to each other that they essentially form an energy band. It needs to be emphasized here that the formation of such energy bands is possible primarily for the valence electrons that are relatively loosely bound. That is very important to the nucleus, as they reside in the outermost shell. They only can rotate around all the nuclei which have been brought close to each other as the solid is being formed, which is actually the packing of many atoms very close together in a tiny volume. Now clearly, wave functions of the inner electrons belonging to different atoms forming a solid exhibit very little overlap, and consequently energy levels of inner electrons do not exhibit any splitting when the atoms are brought closer to each other, because they are very strongly bound to the electron, the inner electron, to the nuclei, the inner electrons. So the wave functions of these electrons do not overlap greatly with the wave functions of the other atom which has been brought closer. That is simply because this is very strongly bound to the nucleus, to which it is much closer compared to the valence electrons, which reside in the outer shell or subshell. Now, in order to appreciate the bearing of the formation of energy band by the valence electrons on the conductivity of a solid, that's what we want to actually find out. We consider the typical case of a sodium atom that has an atomic number of 11. Already, we have seen that the electrons are distributed in the sodium atom in this manner. That is, the 11 electrons, it has 11 protons, which I am indicating by E plus. This doesn't mean that this is electron. This only means that its charge is a positive charge. An electron has a negative charge. This is proton, its mass is much too large compared to that of electron. So out of this 11 electrons, as we have seen, the first energy level, which is n equal to 1, which is only one subshell that has two electrons, which can be indicated as 1s2. Then the n equal to 2 orbit has two subshells. This is 2s, so it has two electrons. And then the next is L equal to 1, that is p subshell. It has 6 electrons, 2p6. So 6 plus 2, 8 plus 2, 10. 10 electrons are distributed within these two, n equal to 1 and n equal to 2 energy levels. Then comes the third level, n equal to 3. So you have now only one electron. So it goes in the first subshell, which is S, and it will be indicated as 3s1. Now this subshell can actually contain two electrons, but only one electron appears here. So this is actually half empty, partially full. So then of the 11 electrons that an atom of sodium possesses, 10 fill all the available slots in the first and second shells. And the 11th electron therefore reside in the L equal to 0 subshell of the third shell, and thus is represented as 3s1, and it actually is half full because two electrons can go. So now let us explain based on this knowledge as to why sodium is a metal. And this will help us understand how certain materials behave like a semiconductor. So you see, as seen, the shells with principal quantum number 1 and 2 are full for sodium, and the outermost soft shell, that is n equal to 3, L equal to 0, and accordingly denoted as 3s, is only half full because two electrons can go there. As only one electron resides there, while the occupancy of the S subshell is 2. Now this being the valence electron, this is the outermost electron. The sodium atoms get closer to form when sodium atoms gets closer to form a solid, the 3s energy level will be broadened, forming an energy band, just as we explained in case of the hydrogen atoms when they are brought close together. So similarly, when two sodium atoms, this is sodium atom, are brought closer to each other, then this ground state, that is that 3s energy level, would be actually broadened, as is shown here. This is actually broadened when they are brought closer to each other, just as it happened for hydrogen, when two hydrogen brought close to, not two, many. So same thing happens for this sodium, the outermost energy level, which is where the electrons are most loosely bound. But the inner levels, so inner levels, that is 2p, 2s, and 1s, which are much closer to the nucleus. The inner levels, that is 2p, 2s, and os, being closer to the nucleus, so to the nucleus, do not show, shows insignificant broadening of the energy level. So they practically, just as they would have been in case of isolated sodium atom, they don't show any broadening. Even when a modest potential difference is therefore applied across a block of sodium, the 3s band electrons can readily acquire energy while still remaining in the same band, because it can actually move within this band even with a very little energy, because it stays within this same band, and it is half empty, it's only half full. Therefore, even with little energy, the electron can actually move around in the sodium materials, in a sodium block. If we just apply little potential difference, the ensuing drift of the valence electron therefore constitutes a net electric current. It is not therefore surprising that sodium is a good conductor of electricity and is accordingly classified as a metal. Now let us see why are certain materials insulators. You see, in the case of an insulator, on the other hand, the outermost soft shell is completely full, and in turn, the valence energy band here is thus fully occupied. To, to further elaborate it, suppose sodium has a total number of, sodium has an atomic number 12. Just suppose, consider atomic number 12. So then it will have 12 electrons to be accommodated. So of which 10 has already gone here. So 1s2, 2s2, 2p6. So 6 plus 2 plus 2, 10 are already gone. Then here in the third orbit, the S subcell, you have 2 more electrons to be placed. So it goes into 3s2. So that entire, it is full. Now there are 2, it can go, 2 electrons can go there, and therefore it is completely full. If the sodium, instead of 11, would have an atomic number of 12, then its outermost shell would be full. So then what will happen? If we apply a small voltage, can the electron take energy and start conducting? No. There is no space for the electron in the energy. Everything is closed. It is a closed shell. So the next energy level is P energy level, which is somewhere here. And this, of course, also can make a band, because it will be even outer. So even it would be even further away from the nucleus. If there were an electron, it would be even loosely bound. So for the electron to conduct, it has to first acquire enough energy to be able to jump up into this. And then only it can conduct electricity. So I think with this analogy, you will be able to understand why certain materials are insulated. So in the case of an insulator, on the other hand, the outermost soft shell is completely full, as you can see here. And as we just showed, in case sodium would have an atomic number of 12. And in turn, the valence energy band here is thus completely occupied, fully occupied. The next outer subshell that is completely empty and has the potential to function as a conduction band, because if the electron comes here, then it is even further away from the nucleus. So it will be even more free to move. But it is separated from this valence band by forbidden energy gap. This gap is forbidden. Electron cannot go there. we know from Bohr's theory. Often measuring several electron volts, this difference is several electron volts. Electron volt is a measurement of energy, and 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. So this gap is several electrons. Now, we will have an idea of electron volt if we can consider in terms of thermal energy. You see, the average thermal energy under ambient conditions is only about 0.025 electron volt, 0.025 electron volt. The valence electrons are unable to appear in the conduction band by climbing over the forbidden energy barrier. So even at room temperature, that is 27 degrees centigrade or 300 degree Kelvin, with this much energy that is always available as thermal energy, electron cannot climb up here because this thermal energy is just 0.025 electron volt, while this gap is several electron volts, say 3 electron volt. So this energy is much too less compared to this. So with thermal energy, the electrons from the valence band cannot climb up, cannot cross this barrier, reach the conduction band. Nor can they cross such an energy barrier by the application of an electric field of reasonable magnitude that readily sets in current to flow in a metal. In a metal, because this is empty, in a metal, this is empty. So even a very small, insignificant voltage that is applied can cause these electrons to move around in this empty space in energy. So the voltage that would be required for an electron from the valence band to cross over into the conduction band can be extremely high. Let me explain to you in a little greater detail as to why the field that is required for putting an electron from the valence band to conduction band for a typical insulator should be so high. You see, this is the valence band and this is the conduction. The valence band for an insulator is completely full. So if this has to be brought into conduction, this insulator, then the electron from the valence band should be taken into the conduction band. Once in the conduction band, then it will be able to conduct current there, even with once it is in conduction or with application of little potential difference. Now, for this electron to be taken to the conduction band, you must be able to apply enough field so that the electron experiences enough of acceleration, allowing it to move from the conduction valence to the conduction band. Now, if we consider in terms of the orbit of the electron, so valence band, so this is the nucleus and this is the outermost shell of the electron, where the electron is rotating. And the conduction band corresponds to, so this orbit. So this orbit has a radius of r1, that is the valence band orbit, and this is the orbit radius r2. This is the nucleus. Now, the electron from here has to be taken to this orbit. It will jump this energy barrier, this energy. That means it has to go from this valence band orbit and this is the conductor. So the force, if we apply an electric field E, then the force the electron will experience E into E. And if this difference is D, then this force must be able to do an work which is E into E, the force into this displacement, which must be equal to the band gap energy. Suppose this energy is 5 electron volt. So this must be equal to 5 electron volts. So if I write it in terms of joule, so it will be 5 into 10 to the power minus 16 joule. So what will be the electric field? Electric field E will be equal to 5 into 10 to the power minus 16 divided by E. E is 1 into 10 to the power minus 16 coulomb into D. D is basically R2 minus R1. So this is equal to 5 by R2 minus R1 will be equal to volt per meter. So for typical insulator, if we from Bohr's theory, you can work out R2 minus R1, and if you plug in these values, we'll see that this voltage is coming to the tune of 10 to the power 6 volt per meter, that is million volt per meter, which is exorbitantly high, and it is impractical to apply such enormous field and make a insulator a conductor, a metal. So then the electric field of magnitude to the tune of tens of millions volt per meter is needed for an electron to jump from the valence band conduction band to a typical insulator. So that is why certain materials behave like insulator. Now, what makes an insulator behave like a semiconductor? So you see, there is yet another kind of substance called semiconductor that also has a fully occupied valence band like an insulator, but quite unlike it. The empty conduction band here is located only marginally above the valence band. That is, the forbidden energy gap here can be even less than 1. It is less than even 1 electron volt. Could be much less than 1 electron volt. Such a material, although behaves like an insulator at low temperature, but at room temperature or above is or above, slightly above room temperature, a small fraction of the electron in the valence band has enough thermal energy to cross over to the narrow energy barrier and enter the conduction band. Once it enters the conduction band, it can, with little application of little potential difference, it can conduct electric current just like matter. Although small in number, these electrons are still good enough to manifest as a flow of current in the conduction band upon application of a reasonable electricity, just like a metal. But the story does not end here. As in contrast to a metal, the semiconductor carries current not only in its conduction band. This is the conduction band where this electron can conduct electric current. You see, the electron, by jumping from the valence band to the conduction band, leaves behind an unoccupied state in the valence band, which is called a hole. These holes, therefore, can basically be regarded as a deficit of electron, and thus will equivalently possess a positive charge. Positive charge. Just as the motion of electrons in the conduction band results in the flow of current. The flow of current in the valence band too arises from the motion of these holes. So you see, the semiconductors are actually much more than just a metal. Metal, the conduction occurs only due to the flow of electrons in the conduction band. But in a semiconductor, the conduction occurs not only as a flow of electrons in the conduction band, but also the flow of holes in the valence band. This is what makes semiconductors much more interesting than that of a metal. So I will end here today, and the next class we will take a more deeper look at the way the hole conducts electricity in a conduction band.